All right, let's dive in. Today we're talking landslide susceptibility.
Mm.
Specifically, there's this new model, and it's claiming to be like way more robust than anything we've had before.
Oh, yeah.
That's pretty cool. Our source is a 2024 research paper
Which
from the Bulletin of Engineering, Geology, and the Environment. And we're going to be exploring some really interesting questions.
sounds good.
Like, how much does slope angle actually matter?
Mm.
You know, is a forest more or less susceptible to landslides than like a barren hillside?
Interesting.
And then there's this thing called, get this, Level-2 Firth's bias-reduced logistic regression
Wow.
model, BLR for short. Don't worry, we'll break down what all that means.
I'm intrigued. It's a really fascinating area of research, especially when you consider how much of an impact landslides have globally.
Yeah.
And this study is focused on Korea, with its mountainous terrain and all that intense rainfall. It's a particularly vulnerable area.
Right.
And they zoom in on Busan, which is Korea's second largest city. So the stakes are pretty high.
Exactly. And what I like about this paper is that it's not just like theoretical. It actually gets really hands-on with a case study
Oh, but cool.
on Mount Seunghak in Busan.
Yeah.
And get this, they've analyzed landslide data going all the way back from 2006 to 2019.
Yeah, that's a lot of data.
That's a pretty substantial data set.
It is.
Before we jump into their model, though, can you give us a quick overview of like what landslide susceptibility mapping even is?
Sure. Basically, it's all about identifying areas that are prone to landslides
Okay.
based on different factors.
Makes sense?
You can kind of think of it as like a risk assessment for hillsides.
Okay, got it.
There are different types of models you can use.
Yeah.
Some of them are qualitative, meaning they rely on expert judgment, while others are quantitative, which means they're crunching data. This particular study uses a quantitative approach.
Okay, that makes sense. So can you like paint us a picture of Mount Seunghak? What kind of geological situation are we dealing with here?
Well, picture this. Volcanic breccia and andesite. These are rock types that are known to be really susceptible to weathering.
Interesting.
And the landslides they observed in this study were mainly shallow translational slides. So imagine a layer of soil detaching and sliding downhill, often triggered by heavy rainfall.
So they're not talking about like massive catastrophic landslides then?
Not in this study.
Okay.
They're focused on a specific type of landslide that's common in that area.
Gotcha.
And to predict these slides, they looked at 11 different environmental variables.
Wow.
Some of them are pretty obvious, like the slope angle. The steeper the slope, the higher the risk.
Yeah.
And then there's curvature, which affects how water flows over the surface.
Okay, yeah, those are kind of intuitive. But what are some of the like less obvious things they considered?
Well, they looked at things like drainage proximity.
Okay.
So how close that slope is to a stream or a river.
Right.
They also factored in soil type.
Yeah.
And even forest type. It turns out that the type of forest cover can actually play a pretty big role in stabilizing those slopes.
Oh, wow. I wouldn't have thought of that. So how did they make sure all these different variables were like playing nice together and not messing up the data?
That's a good question. They had to carefully check for something called multi-collinearity.
Okay.
Basically making sure the variables weren't too closely related to each other.
Right.
Because if they were, it would really skew the results.
Yeah, they had to get like a clear picture of the data.
Yeah.
Okay, enough build up. Let's talk about this Level-2 Firth's bias-reduced logistic regression model, BLR.
It's quite a mouthful, isn't it?
It is.
It's a modified form of logistic regression
Okay.
that's designed to improve accuracy and tackle bias, especially when you're dealing with smaller data sets.
So, like, why is this BLR model supposedly better than just standard logistic regression?
Well, the level 2 part of the name is really key here.
Right.
It means the model can actually take into account the interactions between the different variables. So it can make more nuanced predictions. It's not just looking at each factor in isolation, but rather it's figuring out how they might work together to influence landslide risk.
So it's like a more sophisticated analysis.
Exactly.
I'm guessing they put this fancy new model head-to-head against the standard one?
You bet they did.
Okay.
And they used both random and spatial cross-validation to evaluate how well each model performed.
So can you explain what that means? Like, what is cross-validation?
Yeah, think of it like training for a marathon.
Okay.
You wouldn't just run the whole course once and call it a day.
Right.
You'd break it down into smaller segments, practice on different types of terrain, and see how your body responds.
Okay, so they're putting these models through their paces to see how they hold up. What's the difference between random and spatial cross-validation, though?
Good question. So In random cross-validation, you're shuffling the data and splitting it into these training and testing sets, and you're doing that multiple times.
Mm-hmm.
With spatial cross-validation, they create clusters based on location.
Okay, so you're considering the geographical relationships within the data.
Oh, so like you're training on different types of terrain.
Exactly,
Like
yeah.
hills, flats, maybe some rocky trails.
Exactly. So you're getting a more comprehensive picture of how the models perform across different spatial contexts.
Okay, that makes sense. So random cross-validation is like mixing things up, and spatial is keeping things geographically organized. But how did BLR do against the standard model in all these tests?
Well, BLR did exceptionally well. It scored excellent in both types of cross-validation.
Wow.
It consistently outperformed that standard logistic regression model.
So BLR like took home the trophy.
Pretty much, yeah.
That's impressive. So can you tell us a bit more about how they actually use these models to create like a landslide susceptibility map?
Sure. So they took the output of that BLR model,
Okay.
which is essentially a probability value for each location on the mountain.
Okay.
And they turned that into a visual representation,
Okay.
kind of like a heat map. So they took all this like complex data and turned it into something that's easy to understand visually.
Exactly.
Oh, okay, cool.
And they classified these probability values into different risk categories.
All right.
Very low, low, moderate, high, and very high.
Uh-huh.
And then they use colors to represent these different levels of risk on a map.
Oh, that's really cool. I mean, this could be so valuable for like city planners in Busan.
Right.
They could use this to see which areas need like closer monitoring,
Yep.
avoid construction in high-risk zones,
Yeah.
or even like plan evacuation routes.
Absolutely. It's a powerful tool for proactive risk management. And speaking of the map itself, it actually revealed that the areas with the highest susceptibility were concentrated along the steepest slopes,
Okay.
especially those that were close to drainage channels.
So like where those two factors, slope and proximity to water, kind of come together,
Yeah,
that's where the risk is highest.
precisely. And interestingly, a lot of these high susceptibility zones were actually areas that had already experienced landslides in the past.
Oh, really? So like the model's predictions actually lined up with what had happened in the real world.
It did. It really suggests that the model is effectively capturing the factors that contribute to landslides in this specific environment.
That's really cool. It's a good sign, right?
It is. But it's also interesting to look at the areas that the model classified as lower susceptibility.
Yeah, what did the map tell us about those areas?
Well, those tended to be on gentler slopes. They were farther away from those drainage channels, and often they had denser vegetation.
Oh, interesting. So like those mitigating factors, less steepness, less water, more root stabilization from the plants, they all seem to be doing their job.
It seems so, yeah. It just highlights the importance of looking at the whole picture.
Yeah.
Not just focusing on those risk factors, but also considering the things that might actually lessen that risk.
Right, right. Okay, but we were talking about those like intriguing response curves earlier.
Yeah.
Can you kind of expand on that a bit? What do those tell us?
So these response curves,
Mm-hmm.
they basically provide a visual representation of how each environmental variable influences the probability of a landslide happening.
Okay.
So it's not just knowing that slope angle matters,
Right.
it's actually seeing how much it matters and how that relationship changes across different slopes.
So it's not just a simple like steeper equals riskier situation.
Right. So for example, the response curve for elevation showed a pretty surprising pattern.
Oh, really?
Yeah, landslides were most likely to occur at mid-elevations,
Huh.
with lower probabilities at both the highest and lowest elevations.
That's kind of unexpected. I would assumed that like higher elevations would just always be riskier.
Yeah, it seems pretty intuitive. But in this study, it was those mid-elevations that really stood out. The researchers actually speculated that this could be due to like differences in vegetation
Okay.
or soil properties at those higher elevations.
Interesting. So those other factors might be counterbalancing the effect of the elevation in those areas.
Yeah.
What about like the shape of the slopes, and the impact of water flow? What did the response curves tell us about that?
Well, they found that concave slopes, where water would tend to collect, were more susceptible to landslides than convex slopes where water would flow away.
Ah, that makes sense. If the shape of the slope is encouraging water to like pool,
Yeah.
it makes sense that the risk would be higher.
Correct.
What about proximity to drainage? Did that follow like a predictable pattern?
It did.
Yeah.
The closer a slope was to a stream or a river, the higher the landslide risk.
Yeah.
Which makes sense when you consider that areas closer to water would experience more prolonged periods of saturation, which can weaken the soil.
It all comes back to water, doesn't it?
It really does.
Whether it's the shape of the slope, the proximity to a water source, or the type of rainfall, water seems to be like a major factor in landslide susceptibility.
It definitely plays a significant role. And these response curves really allow us to visualize those nuances
Yeah.
of how these factors interact. But remember, the model doesn't just highlight the risks.
Right.
It also emphasizes the importance of those mitigating factors we talked about earlier.
Right. So things like gentler slopes, denser vegetation, being further from drainage channels, those can all kind of help decrease the risk. It's about understanding the full picture, not just focusing on the scary parts.
Exactly. This research doesn't just identify problems, it also highlights potential solutions.
It really does seem like this BLR model offers a much more nuanced and accurate way to assess landslide risk. But I'm curious, beyond all the technical stuff, what are the practical applications of this? How does all of this translate into real-world action?
That's the exciting part. This type of model has the potential to completely change how we approach landslide risk management.
Okay.
With better predictions, we can actually shift from just reacting to landslides after they happen to actually anticipating them and mitigating them beforehand. Oh, wow. So we're going from being caught off guard to being prepared.
Exactly. And that has massive implications for so many things, from urban planning and infrastructure to even emergency response.
Yeah.
Imagine city planners using these models to, avoid building in areas that are identified as high risk,
Yeah.
potentially saving lives and resources.
It would be incredible to see these models actually being used to guide development and keep people safe.
Absolutely. And think about emergency managers.
Yeah.
They could use these real-time predictions to issue timely evacuations,
Right?
getting people out of harm's way before disaster even happens.
Wow. That kind of foresight could make a huge difference, but wouldn't actually using this model require a lot of data
Well, yeah,
and expertise? Is it something that can actually be implemented on a larger scale?
that's a good point. Implementing this kind of model does require resources, for sure.
Right.
Things like data collection, expertise in GIS and modeling, and the ability to actually interpret and act on those results.
Yeah. But the potential benefits are significant enough to warrant those investments, in my opinion.
It sounds like it could be a game changer in the field of landslide risk management. But is this BLR model ready to just be rolled out everywhere, or is there still more research that needs to be done?
Well, while the results of this study are super promising, it's important to remember that it was conducted in a very specific location with its own unique set of characteristics.
Right.
So more research is definitely needed to see how the model actually performs in other environments
Okay.
with different geological formations, climates, and land use patterns.
So it's not like a one-size-fits-all solution.
Not quite. But it does provide a really valuable framework that can be adapted and refined for different contexts.
Yeah.
And actually, the researchers themselves acknowledge some of the limitations of their study and highlight areas for future research.
It's nice that they're taking such a rigorous and transparent approach.
Yeah.
It definitely makes me more confident in their findings. Before we wrap up, is there anything else that kind of stood out to you about this research?
Yeah, I was really impressed by the emphasis on validation.
Okay.
The researchers really went above and beyond to make sure their model wasn't just some theoretical idea, but that it was actually a practical tool. They used multiple different methods to test and verify their findings, including actually comparing their model's predictions to actual landslide events.
It's like they were saying, we're not just playing around here, this model can actually predict real-world events.
Exactly. And that commitment to real-world validation really makes their findings all the more compelling.
So for our listeners who are now thoroughly versed in landslide susceptibility and the wonders of the BLR model, what's the key takeaway here?
I think the biggest takeaway is that we're really moving toward a more proactive and informed approach to managing these landslide risks.
Okay.
We're not just at the mercy of nature anymore.
Right.
We have the tools and the knowledge to anticipate, prepare for, and mitigate these hazards.
It's a good reminder that, science can empower us to make better decisions and build a safer world.
It really can. And as we learn more about how these natural processes actually work, we can continue to refine our models and our strategies, which should hopefully lead to even better outcomes.
Yeah, absolutely. So, dear listeners, next time you're out and about, take a look at the slopes around you with, like, a newfound appreciation for all the forces that are at play.
Yeah.
Consider what you've learned about, like, slope angles and drainage.
Vegetation.
Yeah, and all those other factors that contribute to landslide susceptibility.
And remember, while we're making amazing strides in understanding and predicting these landslides, it's always wise to just be aware of your surroundings
Yeah,
and stay informed about potential hazards in your area.
well said. And on that note, we'll wrap up this deep dive. Until next time, keep exploring
Keep learning.
and stay curious.